Yes, to give this talk. I think many of you know Sean very well. He is an internationally renowned um, uh, researcher in the field of membrane technology and for the water treatment, wastewater recycling, and desalination. He is the, I think, founding member of the UTS Center for the Technology in Water and Wastewater Treatment. And over the last few years, he is our president of MSA. And his leadership on MSA significant change. We, I think, also actually in this year, we successfully secured funding to establish a new ARC hub for a new trend in the circular economy. I think it's one of the promising direction for Australia to improve its sustainability. Sean is also very productive. I think so far he has already published over 400 papers, which attract I think around 20,000 citations. And he also has been organized by a number of organizations as one of the highly profile research, particularly in the water field. And before I hand over to Sean, just to let everyone to announce a few, I think, housekeeping rules. So please keep your microphone muted. And if you have any questions, please put in the chat box. And you do not need to wait the end of this talk. And you can put actually your question at any time during this short talk. Now let's stop here and back to Sean. Sean, it's yours. We are looking for your wonderful talk.
Thank you, Shiwan. Good morning, everybody. Thank you for coming for the last webinar series organized by ARC Energy Separation and the Monash University and Membrane Society of Australasia. Also, I'd like to thank you, Shiwang Jiang and then Sue, having successfully organized this webinar for the last 2 years, and very much appreciate their contribution. So today my talk is about nutrient in a circular economy. So I will discuss for next almost half an hour. So what's the circular economy and resource recovery and nutrients in a circular economy? What's the challenge for opportunity and for our urine nutrient recovery system? Also, what's the gap to reach the marketable urine technology? Also, what we have developed from our research hub. Also, case studies in the world, what's going on for different application of the urine diversion system. And then after this technical presentation, during my last 6 years MSA board member service, as well as 3.5 years the presidentship, I must say thank you so many people. So I like to show some of my pictures and photos, what we have done for the last 6 years with me, and then I will just want to say thank you to almost for 10 minutes. So that's all about today's presentation. So a circular economy is an economy and that tackle the global challenge like climate change, biodiversity loss, and waste and pollution. On the other hand, the resource recovery is using waste as input material to create the valuable product as new output. So if you look at this circular economy concept, so we first consume and collect and sort waste and recycling, try to maximize our natural resource utilization, and then how to design circular economy, and then we can try to minimize our waste. So that's the burning issue because it can save our resources. Also, we can minimize our waste. So this is one of the new trendy topic for the future our research area. So we especially want to focus on the urine because urine contains very high concentration of nutrients, nitrogen, phosphorus, and potassium, also micronutrients. So you can see that different metals and micronutrients can be utilized from our urine. Also some of the harmful compounds, some bulk organics, micropollutants, and pathogen have to be removed from urine fertilizer utilization. So if you look at the current our nitrogen and phosphorus life cycle, so we are live in the linear economy. So we produce the nitrogen from the Haber-Bosch process and capturing the nitrogen to urea and ammonia, and phosphorus from the phosphorus rock, and then we produce the food and we just consume, and we produce a lot of nutrient to wastewater and contaminate to the waterway to generate the algae blooming. Also we produced a lot of greenhouse gas, CO2 and N2O. So this is not a circular economy system. So we are living in the linear economy. So our project is about how we can make sure this linear economy to circular economy. So if you look at the fertilizer market, so $155 billion, also global shortage of the nitrogen and phosphorus. So our urine could potentially cover a large portion of total market and the liquid market, assuming the full recovery. So when you consider wastewater and urine, so urine is only less than 1% of water volume, but when you look at the nitrogen and phosphorus micropollutant concentration, the fraction is more than 80% of nitrogen, 65% of phosphorus, and 50% of micropollutant. So that we have to focus on to remove this urine, which will reduce a lot of loading for wastewater treatment plant, especially as population and industry grow. So our wastewater treatment loading is much higher than in the future. That's the reason why if we cooperate together with the urine diversion, this will resolve so many infrastructure generation of our future variation. So urine diversion can enhance the food security, reduce the energy by Haber-Bosch process, as well as the wastewater treatment plant aeration for nitrification, and reduce the water consumption, ultimately improve the water quality. That's the reason why we have investigated the urine diversion, how to optimize this process to create the circular economy system. So we collect the urine, produce fertilizer and food, and then we can keep circulating this system to minimize our environmental and economic impact. That's the reason why we have conducted some of the research. So who are doing this urine diversion internationally. So Swiss, they have EWAG, and then the building has a urine diversion system to collect urine and produce fertilizer. Also Sweden, US. Also this is the largest urine diversion organization, Rich Earth Institute. So they produce the fertilizer from urine to make this technology happen. Also try to convince the supply chain of this urine to fertilizer conversion. So this is the next generation of urine diversion toilet. It just arrived. So this is the traditional urine diverting toilet. So if you think about the male urinal, already male urinal without water, and then we can easily collect your urine from the male toilet. Also, this female as well as the unisex urine diverting toilet used to have a small hole at the front of the toilet, and they collect urine, and then feces can be collected at the behind. And this is the new generation of toilet. So we have this kind of small urine diversion line. So surface tension can collect urine to have separated your container. Also you have a feces, and then water can wash out your feces to the different channel. So you can easily select your urine diverting toilet to have your own way of the urine separation. So if you look at the urine, so let's think about the chemistry. What's going on in the urine compound. So when you have a very fresh urine, so you can see the yellow color. So this contains urea, nitrogen, phosphorus, or some of your micro pollutant as well as micronutrient. And if you don't expose to the microorganism or urease, so this urine will just change the color from yellowish to brownish. So this is the oxidized condition. And then when you contact your urine to urease or bacteria which produce the urease compound, so your urine will start to hydrolyze, which means the urea will change to the ammonia. And then this urea will precipitate because of the hydrolysis. You have a high pH from pH 6, and then this hydrolyzed urine will have more than pH 10. So you can see the precipitants. So this is the strobide, and then calcium phosphate, calcium carbonate. So a lot of crystal solid fertilizer can be produced from this hydrolysis. And then when you have more aging of the bacteria, so you will create the more precipitant. Also you will convert your ammonia to nitrate. So that's how this urine can be utilized for your solid fertilizer at the bottom, as well as some liquid fertilizer from ammonia to nitrate. Some of the micronutrient can be collected from your liquid urine. So if you look at the marketable urine, so strobide also have been provided for the fertilizer. Also nutrification using the microorganism. So liquid fertilizer and distillate process, we can produce the concentrated fertilizer. Also ammonia stripping. So at the high pH, urine can be also ammonia will be volatilized, and then you can put the hydrogen sulfide will produce the ammonium sulfate, which is one of the most widely used fertilizers. So that's the way we can make a marketable fertilizer from urine. So our group have investigated this urine technology for last 5 years. So we look at the space application to to convert the urine to fertilizer or wastewater treatment, and then how to hydrolyze our urine and dilute the fresh urine, also power generation using the reverse electrodialysis, also biomass, so we can produce the fertilizer to feed your algae, and then we can have a more dewatering as well as some production of biodiesel. So we have published a lot of papers from this targeted water, nutrient, energy recovery. But today, just because of time limitation, I want to focus on hydrolyzed urine. So this is what we have developed, membrane bioreactor, membrane distillation for the production of concentrate fertilizer. So we collected urine from our university building, and then we conducted some of the membrane bioreactor and then membrane distillation. So our questions were, are the odor and organics in the urine removed? Is ammonia converted to nitrate? So how much we can convert? Because ammonia is still not stable. Depending on pH, this will create the volatilization. Also, a lot of people smell this is the toxic kind of a stinky smell of the ammonia. So we need to convert ammonia to nitrate as much as we can. Also, treated urine concentrate to a fertilizer level. Also, is the final product effective in growing some of the vegetable? So we try to answer this question. So this is our university faculty of engineering. So we have a 15 story to collect our urine. So every day we have collected 2,000 liter, and then this is our pipeline to collect our urine, and then we connect the membrane bioreactor to remove organic acidification, ammonia to nitrate conversion, and then we concentrate this permeate to membrane distillation to further concentrate, also produce the distilled water, and then thermal sanitation is one of our incentive for this process. And then we produce the concentrate fertilizer and grow some of the vegetable. So this is the MBR performance in terms of total nitrogen removal, and then ammonia and nitrate concentration, and then conversion rate. So most of TOC can be removed more than 95% for the almost long-term our operation. Also ammonia to nitrate. So we try to convert from urea to ammonia, ammonia to nitrate, and then we have investigated what's the conversion rate. And then we found out the ammonia to nitrate conversion rate is almost 40% to 50%, which will be the ideal. We try to increase the more conversion, but because of the alkalinity consumption, so that's the maximum we have identified for the conversion rate of the ammonia to nitrate. And then we tested the membrane distillation. So this is our typical membrane distillation DCMD operation. So from the beginning of the urine concentration, we got almost 15 RMH from our flux, and then as time goes, the urine concentration 20%, 6%, and then when we reach to almost 80%, so we found out some of the significant flux decline because of the crystallization of our urine, which is strobite and calcium carbonate have been mainly identified from the surface of our membrane distillation. And then urine concentration increased up to 250 microsiemens per centimeter. So we achieved 95% of the urine concentration. Also severe flux decline at 80% of the urine concentration. So this is the fresh urine, and then concentrated urine, and this is our MD permeate, which can be used for our toilet flushing and recycled water. And this is our concentrated fertilizer, different nutrient concentration. Electrical conductivity more than 250 microsiemens, pH is 4.5, and the ammonia and nitrate. So mostly almost we have 60 gram per liter of ammonia concentration, and phosphorus is around 5 gram per liter. Potassium is almost 18 gram per liter of fertilizer we have produced from this concentrate urine, which are very much useful fertilizer. Also, we have a lot of micronutrient, magnesium, calcium, and some of the iron, silica from our urine fertilizer. And then we have tested the different lettuce and the pak choy hydroponically, and then we compare with the experimental fertilizer and then commercial fertilizer and our fertilizer, and then we found out our fertilizer perform very much similar to commercial fertilizer. So from our initial question, so we can answer this 95% of TOC removal, 50% ammonia to nitrate conversion, 95% urine concentration achieved at 55 degree rejection, ammonia to TOC more than 97%, others 99%, severe membrane fouling, but we recover most of them using 0.1 mole sodium hydroxide. Also, urine contain all the essential elements to grow lettuce and pak choy. So we have successfully demonstrated this MBL MD fertilizer process. So we are continue to scale up for our process. This is the 20 liter of the membrane bioreactor, membrane distillation. Also, we have scaled up 100 liter per day for our generation of the overall fertilizer, which is you are valuable and urine is valuable. So we are testing some of the vegetable or turf or some of the horticultural application, including the flowers. So this is the one of example power feed from commercial fertilizer, our overall technology. So we tested coriander and basil, and then we found out the 21 days, 41 days later, so commercial fertilizer and then our fertilizer have shown the very much similar performance of this fertilizer. Also, we have one of the collaborator who is Stefano from the University of Melbourne. He has tested microbial electroconcentration. So he collected the urine and then hydrolyzed the urine, and we utilized the electrochemical process. So this is the anode and cathode, cationic exchange membrane, anion exchange membrane. The ammonia, potassium, and some of the phosphate and carbonate will pass through your ion exchange membrane, so that we can collect our necessary ionized ammonia, phosphorus, potassium can be collected from this electrochemical process, and we don't need any power because this is the microbial electroconcentration, so we can produce the electricity from this microbial activity. So we have tested this one. Also, if you look at the Australian liquid fertilizer market, so liquid fertilizer is one of the main fertilizer solution. So this is almost $5 for 1 kilogram of nitrogen. So when you consider world population, so we have around 8 billion people live in this planet, and then everybody produced almost average 1.5 liter. And then nitrogen concentration is almost 10 gram per liter. So when you consider all the population, so we can collect 5,000 ton per day, and then 1 kilogram of our fertilizer is $5. So which means every day if we collect the urine and then nitrogen, so we could get the benefit around the $25 million from our urine to collect our liquid fertilizer. So this is our typical urine from the membrane bioreactor and the membrane distillation process. This is the electrochemical process. So electrochemical process little bit less than the membrane distillation MBR process overall TDS. So almost maximum we have collected 130 milligrammes per centimeter, and then total nitrogen 27 and phosphorus 700 milligram per liter, and potassium is not listed here, but almost 10 gram per liter of from this UGOLD system. So depending on your application, yes, you can select the membrane bioreactor, MD, or electrochemical process to apply your fertilizer. Also, we look at the micropollutant concentration. So as expected, there are a lot of micropollutant in urine, and then based on our technology, so we mainly utilize the powder activated carbon or granular activated carbon to remove the most of micropollutant, so that the micropollutant can be handled by the activated carbon to remove the most of very low concentration of micropollutant. So based on this concept, yeah, we have got this ASC industry hub for nutrient in a circular economy, which called AIC NICE Hub. So this NICE project will be a key partnership to transform the wastewater industry and build the confidence for a market in using wastewater and urine as a source of fertilizer for agriculture, horticulture, and parkland. So we have 4 major research themes: how to collect urine effectively and processing to convert urine to fertilizer, how to optimize our urine fertilizer and then apply to agriculture, city, parkland, horticulture, or some of the also application of this fertilizer. And then look at some of the economics, also public perception, and then communication. That's the overall project of this NICE Hub. Also, this is our initial study of the economic benefit. So we can get some of the benefit from the energy cost, 30% reduction in a wastewater treatment plant. Also 75% urine diversion, up to 60% reduction in energy cost possible in the future when nitrogen standard becomes more stringent, and 50% reduction in the freshwater demand. Also we can achieve and reduce the wastewater treatment footprint for new wastewater treatment plant, increase the capacity of the existing wastewater treatment plant. New industry and jobs for urine business can be achieved. Also, we can get some of the environmental impact. So when you consider 90% of the urine diversion, so in the wastewater treatment can save the 40% in house gas emission, 50% of the freshwater use, 40% in eutrophication potential because they discharge the nitrogen and phosphorus less concentration. So that's the environmental benefit we can achieve from the urine diversion. So this is the other application. So this urine is one of our target compound because you can get the high concentration of nitrogen, phosphorus. But when you consider some of the wastewater which contain high concentration of your nitrogen, phosphorus, such as industrial wastewater or livestock wastewater, or the anaerobic bioreactor which contain the very high concentration of nitrogen, phosphorus. So we can combine this technology to produce our fertilizer. Also, we can consider small scale of public toilet. can be combined with this technology to match with some of the green, our flowers or some of the green environment near the public toilet at park. Also, we can utilize some solar dripper. So you can see that this is the urine, and then this is the solar dripper, and then you can combine with your just urine drop irrigation system can be achieved this process. So you can see how to grow the corn using this urine solar dripper. Also, tomato can be grow this using this solar dripper technology with the urine. Also, we have new toilet developed by Swedish group, so Rewise, and they instantly dry your urine from this toilet. So your urine can make your this kind of solid fertilizer as a dry urine, 8% of nitrogen, 80 gram per liter, and then 0.7% phosphorus, 2.7% of the potassium can be drawn from this revised toilet. Also, we have some of the field trial from the US, and they tested with this is the barley to make beer, and this is the no fertilizer, and this is the mineral commercial fertilizer, and this is the urine fertilizer. And then they found out the urine fertilizer shows the best performance compared to others, and then they harvest this barley and then to produce their beer. So that's the urine drive the beer production can be possible. Also, some of the Cornell University, they have a household size of the fertilizer and urine collection and then fertilizer application, and this is the application for the gardening, and then some of the upscale of their urine fertilizer application. Also, corn development of this urine, as well as some of the urine drip irrigation to grow hemp seedlings, which is your cannabis growth of this agriculture. Also, you can see some of the very general application of your fig, and then this is the tough glass. So this is the fertilizer urine applied tough glass, and this is the without the urine fertilizer. So they found out almost 20% green condition can be achieved from the urine fertilizer to grow your tough glass. So this is my presentation. The circular economy and then resource recovery are becoming more important for our environmental and economic benefit. And the urine is liquid gold. So urine diversion can do food security, energy reduction, water reduction, and the urine diversion benefit climate change and circular economy, nutrient resource recovery, eutrophication, wastewater infrastructure. Also, we need to look at the more social, technical aspect. Also, public education and perception will be very important to convince the people to accept this urine fertilizer. I'd like to thank you for our funding organization, ASC Industrial for Nutrient in a Circular Economy. Also, our team members